All right, welcome to Kinetics. This is Zumdahl's AP Chemistry Chapter 12. This is the first of a few on this particular topic. Um, let's get started. So there's a silly quote on the front page. If you want to go back and look at that, you can. That's an original. Gross oversimplification, right? So we've already spoken about the idea that thermodynamics tells us if a reaction can occur based on delta G, Gibbs free energy, but it doesn't say anything about the rate at which that reaction takes place. And so I just pointed out a couple of reactions that are both thermodynamically favorable. One is instantaneous and one is imperceptibly slow. And it's important to note that thermodynamics does not tell us anything about the rate at which a reaction occurs. Kinetics does. Um, First, we talk about reaction rates, is the change in concentration of a reactant per or product per unit of time. We're going to write concentration in moles per liters, where brackets of substance A is a concentration in that value, moles per liters, or that unit. Rate will be a reaction rate. Okay, the rate's going to express the whole reaction, and it's going to be the negative of the change in concentration over time, because since the concentration dips and you would do final minus initial, that value would be negative, and we're wanting a rate that describes the whole reaction that we can then apply to a mole ratio. This is going to give us the average rate of the whole reaction at a certain set of conditions. So this graphic we'll be describing on several slides, so look forward to that. In that graphic, the reaction involved is 2 moles of nitrogen dioxide making 2 moles of nitrogen monoxide and oxygen. On the y-axis, we have concentration in moles per liter. On the x-axis, we have time. So it's a coordinate of the progress of the reaction in terms of concentration, okay? And what you're going to see is we can calculate rates based on a point tangential to the curve at anywhere in the reaction we want. So we can detect a rate of formation, a rate of consumption. We can detect it right immediately at the beginning of the reaction, late in the reaction, whenever we want. But we'll talk about this reaction more. Instantaneous rates tell us, in a forward reaction only, tell us exactly what's going on before a reaction begins. It tells us exactly what's going on at a rate at any given point in time. We compute that by the slope tangent to the curve at that point. This is what I described on the previous slide. And the rate of the reaction at that point is the negative of the slope of the tangent line, because we're going for a positive value that describes the reaction in terms of that particular reactant disappearing. So this is showing how to calculate that tangent line. So you take a point, line tangent to that, and find the slope of it. And this at the beginning would be most indicative of the conditions at which it would be happening in a forward reaction. If we wait a little longer, we're starting to see some of the influences of the products on the production of reactants. So influence the products, influencing the production of more products. So we'll watch as we go forward into equilibrium how we can understand how these impact one another. We're going to be using initial rates in the forward reaction only because initial rates are not being influenced by a reverse reaction. Most importantly, the rate of the reaction is not constant. Rate changes over time because of concentrations changing with time. Those concentrations influence the progress of more things continuing to react on the way to some equilibrium. We will mostly work with reaction rates that are initial rates, where the reverse reaction is negligible because it won't cloud what we're trying to discover about the rate. The initial rate is most revealing to us for the purposes of determining how fast a reaction is going to occur. So when we're examining rates of reaction, back to the curve we were looking at for the decomposition of nitrogen dioxide, we need to make sure we see a couple of things on this graph. Number one, as you decrease concentration of nitrogen dioxide, the reactant, you increase almost perfectly reciprocally in concentrations of nitrogen monoxide, because it's a 1-to-1 mole ratio. It's perfect. Okay, and then you also produce 1 mole of oxygen gas, which is exactly half of the amount of gas produced of nitrogen monoxide. So these physical findings on the graph are the same as what we see in the chemical reaction by mole ratio. So rate laws can express how quickly reactants are consumed or the rate at which a product is produced. We'll focus mainly on consumption of reactants. We have to make the assumption that only the forward reaction is occurring because we would be otherwise clouded by the reverse reaction. So we're ignoring the fact that the reverse reaction could be happening and influencing our rates. Questions on this unit are given to us in a couple of different ways. We can talk about the consumption of a particular reactant, or often the disappearance of a particular reactant. We can also talk about the formation of or appearance of a product. And those are all going to be functions of mole ratio. Okay. Two different ways we're going to look at rate law of this unit. And we've already seen parts of these both in the POGL, but the first, and this is the first we will discuss, is differential rate law, where rate depends only on concentration. And so we'll express rate as a function of concentration, versus integrated rate law, where we actually have time as part of the function. So integrated rate law will come a little later. This is we've already seen a good amount of rate law with our first POGL on reaction rates. Differential rate law is a little bit different, though. Differential rate law is also, we also refer to it informally as a rate equation. We're only going to be looking at concentration. You'll notice in this formula, a rate is equal to K, which is our rate constant, times a concentration A to the power of M and a concentration B to the power of N. We're going to have this reaction with its coefficients and its particles forming products. Notice that in our rate equation, there are no products. We're completely ignoring the products. We're only focused on the consumption of the reactants. Our rate is going to be equal to that rate constant times those values. What you should notice is that M and N, these exponents, are not features in the reaction. They are independent of the reaction coefficients. So these values A and B will be in moles per liter. The values M and N are going to be determined experimentally only through data. They are not coefficients from the reaction. And if you happen to see a question where they end up being the same as the coefficient, that's going to be a coincidence, okay? The exponents are going to be positive or negative. They can be integers or fractions. Usually on the AP test, they're going to be positive integers. 0 to 3 are very common. You may rarely get a fraction as a reaction order or a particular reactant order, but that'll probably be on a free response question if that were to happen. But I guess it's possible on a multiple choice also. The little k is not the same thing as equilibrium constant that we learned in both thermochemistry and in electrochemistry. It is a small k. It's completely a function that is made to equate rate to concentrations based on data. So that constant is going to be a function of those two things, rate and concentration. The value of K is going to depend on the type of reaction, the temperature, and the presence of a catalyst. Those things can influence how high K goes. The faster the reaction goes, the larger the K value is. The exponents that we see, M and N, determine the order of the reactants. The sum of those exponents in order is the order of the reaction. So we can speak about a rate law like this one, rate's equal to the reaction, the rate constant times A times B squared, as this reaction is first order in A, second order in B, first order in A because we have an imaginary 1 exponent here, second order in B, and third order overall. Third order is calculated by simply adding the coefficients. But to make sense of the word order, what it means is if we were to double the value of A, that means it would double your rate. Okay? If a reaction part is second order, like B here is second order, then if we double B, we can expect to quadruple R because of this square. And overall 3 is, if you doubled A and doubled B, you'd get an effective octupling of R. The third order overall means you would multiply your rate times 8 if you doubled everything. And that is completely due to those exponents. And again, these aren't something known. These are something that you would determine from a piece of experimental data. Additionally, we can find the units of K just by looking at what we've got in our rate law. But let's make sense of that too. First and foremost, the units of rate, much like they are in physics, are going to be a change over time. So we have, in this case, a change in concentration molarity over time, right? Well, to simplify that further, we know molarity is moles per liter, and per unit time, in this case, is going to be seconds. It could be hours, it could be days, it could be years, but it's some unit time. So rate is always going to be in moles per liter seconds, all right? Molarity, we already know, is in moles per liter. So we can plug all of our values into the rate equation depending on what our rate law says, and we can calculate the units very quickly in our head for K. So this is the rate equation rearranged for this example we looked at just a moment ago, where rate was equal to K times AB squared. We can simplify that further by plugging all those values in. Here's the rate that we just discussed, moles per liter second, pardon me, divided by 1 molarity moles, this is A, and then the molarity squared, moles squared over liter squared for B. We simplify this and we end up with the following. Our K values units are liter squared per mole squared seconds. And what you should immediately connect is that in a third order reaction, we see that we have liter squared over mole squared times time. So to further explicitly show you, the shortcut for determining units of K is this equation, where K is equal to the volume to some power divided by moles to that same power times time. It's always going to be one less than, the x value is anyway, the x value is always going to be one less than the overall order of the reaction. So if your reaction is third order overall, then your values for your units for K are going to be liters squared per mole squared per unit times unit time. Second order, liters per mole time. First order, just 1 divided by time. Of course, we can go higher than third order, but the rule still applies. If you had an 8th order reaction, then it would be liters to the 7th over moles to the 7th times time. A student asked about it, what does that look like, a liter 7th to the mole 7th time? It's not anything more than a constant used to create an equality between rate and the concentrations of the reactant. That's all it is. It's not an actual thing. It's the theoretical value that creates an equation. Allows us to manipulate values to determine rates or to determine concentrations based on knowns. So I've already mentioned these, but the differential rate law rules for determining reaction order through experimental data basically is this, is if you double the initial concentration of a reactant and the rate doubles, then it's a first order reactant. So whatever manipulation you do to concentration has the same impact on rate, first order. If your manipulation of concentration is squared, for example, if I doubled the initial concentration and it quadrupled rate, that would be second order. If it octupled, that would be third order, and so on. Additionally, there's another way to look at too. There's a possibility that the changing the concentration of a reactant has zero impact on rate, and that's called a zero order reactant. So what you need to know about zero order is quick and easy. Students have asked, does that mean it's a bystander? Is that a wallflower? Is that a compound that is spectating? No, it's not. This is about rate. The substance is necessary in the reaction. It takes part, helps produce products. It is consumed, so it's not a catalyst. But no matter what you've got, that substance's presence does not change the rate. Okay? So zero order reactants are also omitted from the rate equation. So you will omit them from the rate law expression when you finish and determine you have a zero order reactant. Reactions can have fractional orders and orders greater than 3, but the AP tests, they're not that common. We will see a few in practice. So here's an example. We have 2 moles of A reacting 1 mole of B making C. We're not going to focus on C at all. We're only focused on the reactants and how they behave with each other. First thing we must notice is that we're trying to assess the impact of each reactant on the rate. So we need constants and we need controls each time. So with the first example, if we hold A constant from experiment 1 to experiment 2, we note that B is doubled. We're looking for what impact we see on rate, and it doubled. Because the rate change matched the concentration change, that's first order with respect to B. As far as A, we do the same. We hold B constant from experiment 2 to experiment 3, and we note that we have a doubling of concentration of A results in a quadrupling of the rate. Okay, that, since a doubling quadruples, that's second order with regards to A. So, moving through there. Second order, first order in terms of B, and then there's your rate and your overall third order, because the sum of those two exponents, 2 plus 1 is 3, so it's third order. Go one further, we would know that our units for K would be liters squared per mole squared times, in this case, I think it's seconds, but some unit time, whatever it says in the question. If we have A making B, concentration of A changing over time and rate changing, we have a reaction that's made from one atom or one molecule becoming something else. We just look for whatever change we see. When doubling A's concentration, we see a 4-fold increase in product. You need to be careful when you get these Roman numeral, not Roman numeral values, but scientific notation values, that this is 3 10 to the negative fourth, and this is 1.2 10 to the negative 3. So this is essentially 3 and 12. So we have a fourfold increase there. So that leaves us with this. So our rate's going to be a to the x, where a is going to be a 2, because we have a twofold increase making a fourfold increase in rate. The overall reaction order for this one would be 2. Our units would be liters per mole unit time, and that's it. In this example, we have ammonium and we have nitrite ion. And we have a little bit of a typographical error here we need to repair. That's going to be a 2. So what we see, if we hold nitrite constant here, we see that we have no impact there. Sorry. Yeah, no, this is correct. I apologize. Let me start back over. This is not the one I need to repair. I apologize. Everything on this slide is fine. Let's get back to work. Okay, so in the first example, experiment 1, 2, and 3, in the first reaction, we have 0.1 and 0.005 with this rate. Second reaction, 0.1 and 0.01, making this. And the third, we have that value. What we're looking for is when items are held constant, things changing. So we have a constant of ammonium while nitrite's being doubled, and we have a doubling. And then the second example, we have a constant here and a doubling, and we have a doubling. So everything is first order. Since everything is first order, we have an overall second order reaction. This question also asks you to calculate the K value. We can rearrange the rate equation for this to say K is equal to rate divided by A, B. And that will give you a rate of approximately 2.7 times 10 negative 4. And that's going to be, since second order, liters per mole second. Well, actually, it's minutes on your paper. There you have it. We have this example. This is the one we need to repair. We are looking for something being held constant to assess the change in a different reactant's impact on rate. And so when B is held constant, A is doubled, and that has 0 impact. So A is 0 order. When A is held constant and B is doubled, we see a doubling. There we go. So first order with B, 0 order with A, and since we have a 0 order reactant, we know we can omit it from the rate equation. So in this example, we have 5 bromide ions, a bromate ion, and 6 hydrogen ions, making 3 bromine and 3 water. What we need to do for each reactant here is determine what change impacts the rate. So first, for bromide, we have a change here of doubling. We have a constant here and here, and then we see a doubling. So that's first order with respect to bromide. Let's just get the pen back. So there's your first answer. First order, because doubling bromide doubles the rate. Let's look at bromate. We need to look the first and third for bromate. In the first and third, we get a 1.5 change on bromate when bromide and hydrogen are held constant. And just so happens we get a 1.5 change in rate. So that's also going to be first order for bromate. So we're first order here and we're first order here. Then we look at hydrogen. Now, we don't have a scenario where bromate and bromide are held constant, but we do have one where bromide's held constant, so we'll note that. And then look what happens to bromate. Bromate's doubled here. We already know that bromate's first order, so we can expect it to double the value for the rate, okay? And I want to simplify this a little bit. This rate I'm going to call 3,000. I'm going to call this one 375, just to keep my proportions correct. 500 and 250. So we already know that this bromate had doubled this value for rate of disappearance. So we're going to go ahead and have it to just show the influence that hydrogen ion has on the rate. So I've divided by 2, which is going to take away the doubling that bromate would have done to the rate, and it's going to focus us only on what's remaining. So we have 1500 is our new rate. So what change do we see in hydrogen is that it multiplied by 2. So what actually happened between reaction 3 and 4 is it went from 375 to 1500. That's times 4, and that is second order. So doubling hydrogen is second order. Doubling bromide or bromite is first order. So the rate law for that reaction is going to be this. We have 1 each of bromide and bromate, pardon me, and then we have a second order with respect to the hydrogen ion, and that's overall fourth order. We need to calculate K, the rate constant, and what we'll do is simply by plug and chug solve for K. We can choose any of our experiments, 1, 2, 3, or 4, it does not matter which, and it looks like we're really focused on sig figs here, so we got 3 sig figs for each one. But main idea, what are our units for K going to be? Since we're calculating rate constant, it's going to be, since it's overall fourth order, you should expect your units to be liter cubed over mole cubed unit time, which in this case we have seconds again, and that's that. Now, when you calculate K, you get 5,000 liters cubed per moles cubed seconds. That's huge. That's a large number. And the large K tells us what? The large K tells us that this reaction happens almost instantaneously. And that is the conclusion of the first video on Introduction to Kinetics and Differential Rate Law. Please make sure you've taken high quality notes, and we'll work on it more in class.